Okay. Maria Paula?
Yes, can you hear me? Can you hear me?
I think we can start. Here I will put a translation in Spanish for the people, for the students. And you can speak normally in English. I will present you, okay? And we can start.
Okay.
Okay. You can.
Oh, so I'm
share your screen.
disabled. I cannot share my screen. Did you make me host? Andre?
Bien,
Andre?
estimados, vamos a continuar con nuestra semana. Ahora vamos a tener la presencia de la arquitecta María Paula Riggio. Ella es docente, profesora asociada de la Universidad Estatal de Oregon, ¿ya? Especializada todo en el trabajo de estudios en arquitectura y madera, mecanismos y ingenierías de perfiles estructurales, y dicta algunos cursos súper interesantes con el tema de innovación en el diseño con la madera. El día de hoy nos va a presentar sistemas constructivos de madera y cómo se pueden ser implementados como una estrategia lógica y sostenible para la arquitectura moderna contemporánea. Sin más, le agradezco la presencia de María Paula y bienvenida a la Semana Internacional de Arquitectura. Gracias.
Hello, everybody. Hope you can hear me well. I think I'm not able to share my screen, Andre. Maybe you need to make me co-host or something. So while we wait for Andre to make me co-host.
You can share, now you can share
your
screen, Maria Paula.
Okay. Okay. Okay, let me see if I presentation. Okay, so what do you see now? It's the presentation or it's the presenter view? Which one do you see? The first slide?
Moderator mode, Maria Paula, if you can.
Okay.
Yeah.
Okay, and then I have to change. Sorry for that. Okay, what about now?
Now it's okay.
Okay.
No, it's okay, great.
Okay, good. Thank you, Andre, for inviting me today for this presentation and for everybody in the room and online to attending. It's an honor to be part of this third week, International Week by Architecture. So my name is Maria Paula Riggio, and I'm an associate professor in the Department of Wood Science and Engineering, the College of Forestry at Oregon State University. So I'm in the College of Forestry, but my background is architecture. I have a master in architecture from the University of Florence in Italy, and in engineering, I have a PhD from the University of Trento in Italy on timber engineering, and I'm a licensed architect in Italy, a member of a number of international association focused on development of best practices for the built environment and also for the cultural heritage, historical buildings. In fact, my background is related to conservation of the built asset and assessment and monitoring. I'm interested in analyzing performance of timber buildings, of course, wood architecture in general, and I'm also very interested in many aspects of sustainability under this big umbrella that is now known as a circular economy. So basically understanding how we can build a more sustainable built environment, from sourcing the materials to the entire life cycle of a building. So today I'd like to talk about wood construction systems, looking at the evolution of these systems, and I would say also the revolution and the opportunities that these systems bring to us now. So for sure, wood is one of the oldest building materials. Somehow the tree itself with its branches, it's a sort of archetypal tectonic system. But it's also one of the, in my opinion, one of the most innovative and youngest materials, thanks to the development of new engineered wood products, advanced engineering systems, and novel ways of fabrication. I'm sure at this point you have been told about many things about wood and how this is a very intriguing, complex material. Probably you're now familiar with the concept of anisotropy of wood. So if we look at the material at the different scales, from what we see with the naked eyes to the cellular, molecular, and chemical structure, we see that basically nature has engineered one of the smartest material, considering that what function it plays in a tree to support the canopy, and then to allow the transfer of nutrients from the root to the leaves. So these different functions of transport, storage, and of course then the structural function. We see how this has been devised in ways that really optimize the material. So we talk a lot about material and structure optimization nowadays in architecture and in engineering, and nature does this every time. So I want to point out to the this cellular structure with basically a bundle of tubes. We often use the similitude of the drinking straw, and I'm sure my colleague before me used the same analogy. So we have these tubes, and you know that these allow to have this strength along their length, along their axis, while at the same time being very light. So the material is stronger and is stiffer along the direction of these tubes. And I'm not going too much in the details of how this is also somehow reflected at the different levels, at the different scales of the material. But keep this in mind. So we have a strong directional material with the which is strong in tension along the grain. We say along the grain, along this direction of the fibers, while it's weaker along the grain. So if we push this bottle of drinking straw, they will deform, yet they will not fail. But if we pull them apart, it will fail. So tension across the grain is the weakest direction of the material. Another intriguing, fascinating, and challenging aspect of wood is its relationship with water. And again, I'm sure you have been exposed to this concept as well. So we have water in the tree and we have water both within the cells as free water and within the cell walls. So into the cell walls as bound water. This bound water has a huge effect, a huge impact how wood behaves, has impact on its mechanical properties, it has impacts on all physical properties, and also in its dimension. So you know that basically wood always absorb and desorb moisture from the environment, from the surrounding environment. And this implies also changes in its dimensions, and basically these changes are different in the transversal direction, because basically we have these cell walls that will swell as well. So this movement is kind of propagated along the transversal direction, while it is much more stable along the grain. So I just wanted you to keep these things in mind when I will describe some of the construction systems. So first of all, some historical background, and now I'm just focusing on the Western culture, because we have a rich, incredibly rich culture of building with wood also in other parts of the world. But let's focus on some Western traditions. So in those countries where the land was largely covered with coniferous forest, it was logical to use this plentiful source of material for building houses in the simplest way, basically with these massive wood walls, which provide good insulation. And so we have, you know, in these areas of the world, the development of so-called log houses or block bow houses, or this technology that basically use logs, stack them in walls that are intersected at the angle to make sturdy construction with also good thermal properties. On the other hand, in areas with a climate zone which favor deciduous hardwood trees such as oak, different technologies took place that is based on timber framing. So in this case, we have elements that are connected to make a frame, and then other materials that are used for the infill, to close these panels as non-structural materials for the building envelope. And this technology has different names in different parts of the world, but you can find it in different parts of the world. The thing that it's interesting, in which we have earthquake hazard. So it's very interesting to map the evolution of timber framing systems in different areas of the world that are earthquake prone. And so we both share the lack of being in the so-called Ring of Fire, both Peru and we on the West Coast in the US. And I'm pretty sure you know that a technique that is based on the use of timber framing and other light materials, was also common in the past in Peru, the so-called quincha system. And so here are some examples of heavy timber frames in the past. You can date it back to the Opus Graecium from the Roman time. One of the characteristics of these systems is the presence of the cross bracing to create a more stiffer system that can also resist shear forces, so basically horizontal forces. And this type of construction, the so-called heavy timber frame, it's also a common type of construction nowadays, also in the US, particularly for commercial buildings, also industrial buildings. So the characteristic of the heavy timber system is that is also often called post and beam. It uses large timbers from vertical columns and the horizontal beams, which are connected nowadays with wooden, either with wooden joinery or metal connectors. But of course, in the past, carpenters relied heavily on notched connections. So this type of connection system transfer loads through friction and bearing. So basically, again, keep in mind this structure of wood, and with the material that is very strong along the grain. And so the way the load is transferred through this connection is by compression, so compressing the fibers, which allows to obtain a very important behavior, for instance, in case of an earthquake, that is dissipating energy. So basically, we have a ductile behavior of in the connection systems. Now, in case of an earthquake, we also have to make sure that when we have the reversal load, these systems do not disassemble. So we have to secure the carpentry joint somehow. But how did this system required a lot of skills? It were kind of unique buildings. So they quickly there was a development in North America, especially with after the Industrial Revolution, with more efficient cutting of wood into timber members of a smaller cross section, which increased the efficiency and economy of building in timber. And also, it was influential, the invention of the wire cut nail, which greatly increased the availability of nails at a lower prices. And which basically replaced the blacksmith and forged iron nails. So in the early mid 1800, we have the development of the balloon frame, which was originated in the United States around the Chicago area. And this is the St. Mary Church in Chicago is known as the first balloon frame building. So the characteristic of the balloon frame is the use of full height studs. So basically these vertical elements that go for the entire height of a building, and then the floor joists are supported on a ledger. So basically, there is a continuity of the vertical system, and the wall extends to 2 or more stories, and the floor is sunk of a ledger connected to the wall. This system is still used in the US, especially in industrial and retail applications, but it has its advantages and disadvantages. One of the advantages is that we have this continuity of the load-bearing vertical system. So if you, again, keep in mind the anisotropy of wood, we have a continuous load path along the fiber of the material where it is stronger. And also we avoid we have less impact in terms of dimensional changes due to moisture changes. And you will understand this better when you compare this system with the platform framing. So in contrast, by contrast, the platform frame positioned the floor platform between the first and the second floor vertical studs. So you see, we have the joists that is supported by the stud from the lower floor, and then the stud on the upper floor is stands on the floor joist. So we have vertical vertically oriented fibers, then horizontal oriented fibers, and then again vertical. So this area of the floor joist may be deform in case of high loads, because we have crushing of the fibers. We may have high compression loads if we have multi-story buildings, and also because swelling, so this dimension variation due to moisture absorption are higher in the transversal direction. This may also have an impact. This is one or two of the factors that may limit the number of stories in a light frame system. It's not the only factor. In fact, fire is also a huge limiting factor, but I'm not going to talk about this. I just want to show you, all the variations. So an approach to kind of combine the advantage of the platform frame, which is easy and fast erection. In fact, it's the most common way of building in the US for residential buildings nowadays. So a possibility is to still have studs on top of each other, so that we have this continuity of the load path along the fibers, and then have a top flange hanger that supports the joist of the floors. So talking about load paths, so we have the vertical loads that are transferred from the roof to the walls through the studs, and then in the platform system we have the joists in the floors that also transfer the floor loads to the studs of the wall below. So this is the load path, the gravity load path. But then, of course, we have also the horizontal forces. And so the horizontal forces are transferred to the studs through planking, through planar or panelized systems. And the planking transfers the horizontal forces along the wall into the supports, and the stud frame prevents the planking from deforming, from backling. So this means that we have not just linear members in a light timber frame, but also panelized systems. And actually, we have not just what we call here dimensional lumber, which is based on this standardized dimension of timber that is cut in so-called 2 by 2 inches by 2 by 4 by 6. But we have also different types of engineered wood products, which again, especially for higher loads, allow to optimize the material, to use less material, and have stronger elements. One of these common systems used in light timber frame, for instance, for highly loaded floors, are the I joists. in which we have the flanges that can be either solid wood or different types of engineered wood products, and then the webs in which we have a type of engineered wood panels. And these are, in the past, they were made of plywood. Nowadays, they're typically made with type of strand lumber composite. And we have here these two materials that are also used for the planking. But I'm sure you have, at this point, you have some familiarity with these different types of products. In this diagram, I want to show you how you can classify them. So basically, the different types of engineered wood products, what the basic concept is, they are made by laminating wood. Wood in that can be cut, that can be reduced in smaller elements, in boards or in veneers or in strands. Sorry. And so depending on the width of this elemental component and the length of the fiber, we may have different types of engineered wood products and with different structural capacities. I've seen one of the questions regarding the sustainability, why wood is more sustainable. And I like to respond to this later on, but keep in mind this diagram. We have said that wood is strong in one direction, the direction of the fiber. So depending how we layer these fibers in a wood composite, then we will have a material that is stronger in one direction, that may have similar strength and stiffness in two directions if we cross layer the fibers, or that has more like a plate behavior, maybe not so strong, but somehow equivalent in all the direction if we orient these fibers more randomly. And these laminations may be connected in different ways. The most common way is through glue with adhesives, but we do also have laminations that are connected with metal nails, with wooden dowels, or other types of systems. There are multiple advantages of using engineered wood products. One is that wood, among all the other things, is a natural material, so it's variable, it's unpredictable. We may have different heterogeneities that affect its mechanical properties. So if we reduce the size of the material and the occurrence, and basically we spread these heterogeneities in the lamination, we have a much more uniform material, more predictable, something that engineers like more. And then we can overcome the limitation of wood as as it comes from the tree with its the dimensions that are linked to the original dimension of the tree trunk. We can have longer elements by connecting the lamellas through finger joints, so-called finger joints. We can stack these lamellas to make bigger cross-section. We can cross-layer them so that we can have more dimensional stability, because, as I said, there is an anisotropic behavior in the way wood as well and shrinks. And we can even shape it. Like we can have curved elements. We can achieve a lot of architectural new shapes, new forms, thanks to the versatility of these materials. And we have, at this point, a large portfolio of timber members that we can use, of timber systems, both panelized and linear. And we can combine them in horizontal systems, in floors. We can combine them and we can use them in walls, and we can have a combination of linear and panelized systems of different types in for walls and the floors. So with the development of so-called mass timber buildings that use these mass panels or this engineered with panels such as cross-laminated timber, you have seen the previous presentation about it. So the first development used these panels both for floors and for walls, both as a gravity load-bearing system and as lateral force resistant systems. Now you can see some of the potential limitations of this system. That is basically, if you have to have a continuous load path, and therefore you have to have basically the same layout in all the floors. There are some ways to overcome this challenge, but yet these are potential limitations. Other limitations is that you have to have enough material. So also on the external walls to have enough strength in the external load-bearing walls. Therefore, the windows glazing can be, you don't have so much freedom, let's say, in how you place the openings on the facade. There are also lots of advantages, of course, and this building that was was the first multi-story building made with CLT was built at an incredibly high speed and densely built and populated area in London with no disturbance. So in very fast and efficient way. This system is also very interesting in seismic areas because it basically works as a box. So it's very rigid, very stiff, and both the walls and the floor can participate in the transferring the horizontal forces. But nowadays we see more and more the use of a combination of mass timber panels with post and beam systems. Post and beams that can be made with glue laminated timber or other type of linear engineered wood products, and panel floors that can be CLT, double laminated timber, or other technologies, mass ply panels, which have been developed here in Oregon. So really the tendency here is to have hybrid systems in which we have a mix of wood with other materials, or if different engineered wood products used for different structural systems. And I would say this is, in my opinion, the future. We build with wood, taking advantage of all the properties that different materials, or the qualities that different materials can offer. And these are some examples of hybrid mass timber buildings. Brock Commons is a 18-story student residence at the University of British Columbia in Canada. At the time it was built, it was the tallest mass timber structure in the world. And you see that basically there are two main structural systems: a concrete podium and then two reinforced concrete cores where all the vertical distribution elements are located, so elevators and stairs. And then we have the timber support structure with post and beam made with glue lam and other types of engineered wood products in the lowest part where they are most loaded, so-called parallel strand lumber, and then CLT floors, cross-laminated timbers for the floors. This is another building, Carbon 12, which is an 8-story mass timber building with CLT floors, glue lamp, post and beam, and a so-called backline restraint brace frame made of steel for the horizontal force resistant system. This was the tallest building in the US when it was built. And this is the gold building, is one of the new signature mass timber building in the Adidas Portland campus. And again, it utilized a hybrid structural system with precast concrete columns and girders and glue lamp beams and cross-laminated panels for the floors. So this is another picture of the Adidas building, and you may notice another interesting aspect of using this system, which is prefabrication. I'm sure my colleague Michael will talk more about this aspect after my presentation, but this is a huge advantage of building with wood and also in a hybrid systems, the possibility to have a fast erection and reduced or no construction waste, high precision, minimum tolerances, and so on and so forth. So we in the wood construction industry, there is an increasing interest of developing kit of parts. So basically developing construction systems that are based on use of a few standardized elements that are used throughout the building and maybe reused in different combinations in other projects. So while traditional light wood framing is, I would say, a pretty much low technology construction system with all the studs and plates that are erected on site, there are ways to expedite the construction or even push the construction to the plant, and so basically have a off-site construction of the wall panels or of the walls and the floors or of the whole system. Wood by itself has a certain level of, allows for a certain level of prefabrication, especially when we nowadays build with heavy timber framing or mass timber construction. And we can have different ranges of prefabrication from linear, panelized, or volumetric. So in linear prefabrication, for instance, we may have incorporated already in the elements connections. In the panelized, we may have different levels of systems integrations, including the envelope, for instance. And then in the volumetric, we can build from room modules to basically whole houses. These are examples of integration of the building envelope control layers in a light frame wall. So you see that all the functions of the building enclosure are made through a layered system in which we have the light, so the studs and the planking, the sheeting that plays basically the structural role. The sheeting can have also a role as an airtight layer to avoid airflows. And then we have the thermal insulation layer between the studs, protection of the insulation layer, and then a rain screen. In mass timber external wall, depending on the technology of the mass timber panel, this may have different roles, including a certain level of air barrier, and also participate in the thermal in the thermal envelope, because of course wood is a good thermal insulator. So we can reduce the thickness of the thermal insulation thanks to the use of mass timber panels. And we could, and we can, in some cases, there are examples of integration of these systems of the building enclosure in prefabricated systems. This is an example of a project that was developed, was built in Austria in the Alps in 2009, which uses modular CLT to quickly assemble on site rooms for the hotel. So this is in the Alps with heavy snow loads in and early snowfalls. So there is a very limited time span where it's possible to build. And therefore, they wanted to expedite the process. They built all the modules in the plants, delivered and stacked quickly. And so you see that this type of concept can be very, very appropriate for buildings where we have a repetition of the same type of spatial layout. That can be hotels, dormitories, students' residences, and so on and so forth. You see here the two modules that are stacked on top of each other. And in this case, they are almost three-dimensional. One side was open to then attach the facade that was also prefabricated, but was a separated system. And you have the double layers of CLTs that also improves the acoustic insulation between floors. So what we see, it's really what we have seen. It's a transition from craftsmanship, in the old-fashioned heavy timber framing, to mass production with the evolution of the light framing system, to mass customization. So nowadays we can build with wood in a very efficient way, but also have unique projects to a certain extent. So we have almost all the time unique projects, and we are also now trying to investigate how we can have some form of standardization within this mass customization. So you see here new modern ways of building heavy timber frames with mechanical connections, keeping the wood exposed also, that creates very, very beautiful interiors, and connects people with nature and participate to the biophilia of the environment. And connections play an important role nowadays also, not only on the structural behavior of these systems, but also in the expressive, in the architectural expression of these structures. And nowadays, with the development of digital fabrication, the use of computer controlled, numerically controlled machines, we can carve wood to create notch connections with the complexity that it's even bigger than what was possible in the past with the traditional heavy timber frame. So we can shape wood, we can bend it, we can curve it, we can create curved shapes, and we can notch them with CNC machines. And basically, we can have unique pieces, as in this beautiful grid shell by Shigeru Ban, still in a very efficient way of fabricating. So I think wood is really, again, a fascinating, complex material, but really brings a lot of innovation and a lot of opportunities in terms of creativeness. And of course, we believe also will help us to create a more sustainable built environment. So thank you all, and
Gracias,
yeah.
María Paula.
Yes.
Bien, voy a hablar en español para el público que está acá. Hay algunas preguntas que quería comentarte. Hay una pregunta de un docente que comenta por qué la madera podría ser mejor o más sostenible en comparación con el bambú, el material bambú.
Yeah. I'm not claiming that wood may be more sustainable than bamboo. They're both renewable materials. So as long as we harvest wood in a sustainable, we harvest wood in a sustainable way, meaning making sure that all the material that we harvest will be replenished with new plantation, and so that we really have a renewable resource, then this is I think that wood will be definitely a sustainable option in a very comparable way to bamboo. The difference is probably we have much more opportunities with wood. So far, the number of engineered wood products surpasses the number of engineered bamboo products, yet there are some. So bamboo is shares with wood similar strategies that nature devised, the tubular structure, but in wood this is a more microscopic level, and the engineered wood products that have been made with bamboo not necessarily achieve the same quality in terms of strength and lightness that has been possible with wood so far. So I think that rather than speaking about which one is more sustainable, what is possible right now with the technologies that we have, wood has some incredible advantages in terms of workability. So we can make these big panels or big linear members. We can shape them so we can have an incredible opportunity in terms of how we can create spaces, and we can carve it with which it's a little bit more complicated with bamboo. There are other differences. Well, again, the fact that it's a more spread resource allows us to use it in a more versatile way. So we have different species that allow to target, and have more specialized uses of this material. And also, in terms of sustainability, I want to point out that nowadays we use wood from plantations, and also, so it's not virgin forest. It's wood that is basically planted to be harvested and then replanted again. And also there are some, especially for engineered wood products, there is an opportunity to use underutilized resources that otherwise will be just burned because they're removed from forests, for instance, to avoid the risk of wildfire, and the possibility to use smaller logs to make these bigger pieces allows us to basically to make more resilient forest while creating efficient building systems. I hope I responded to your question, but again, the short answer is they're not necessarily one more sustainable than the other one. It's just the range of opportunities that would offers that at this point it's very broad. Other questions?
¿Más preguntas? Una en el chat. ¿Cuál? ¿Lo tiene ahí que no lo veo? Lo borró porque no. ¿Ah? No está. Acá. Otra pregunta, una consulta. En caso de edificaciones mostrados como en la Universidad de Canadá, ¿no serían más propensos a ser vulnerables a incendios? ¿O se aplica algún método de impermeabilización de material para que éste resista al fuego o la humedad externa al edificio?
Okay. So there was a lot of research done for this building, and nowadays we can build these type of buildings in North America in a more expedited way, because thanks to all the tests and data that have been collected. But at that time, of course they had to face the problem of fire, and they one of the ways, so there are basically two strategies to protect buildings from fire. One is the passive strategy. That means avoiding the spread of fire by protecting the material, avoiding the exposure of combustible material. And then the other is active protection with sprinklers and, with extinguishing the fire. So both strategies were used in this building, and specifically in terms of protecting the timber, it was all encapsulated, meaning gypsum board panels were applied to all the exposed surfaces to avoid to reduce the amount of fuel in the building, so the risk of to protect the material. In the code now in the US, it is there are different levels of protection required depending on the number of stories and the type of occupation of the building. But basically, there is an opportunity to leave some of the to leave some of the material exposed, and the code officials are working and believe that in the future will be possible to leave most of the material exposed. Juan Carlos presented before me the behavior of wood that when it's a very when we have enough material, when it starts to burn, that it develops these charred layers, which works as a thermal insulator, so avoid heat to be transferred into the interior of the section, so protects the wood and allows it to resist. So the internal cross-section is still resistant. And this way of designing for fire resistance is a common way in timber building, and allows us to reduce the number of protection, so that the amount of protection. So yeah, both strategies of using sprinklers and encapsulation was used in Brock Common. And regarding moisture protection, there was another interesting strategy that was used, different strategies. One was to build each floor and enclose it with semi-prefabricated wall facade panels. So for each floor, basically, they were trying to protect the floors from wind-driven rain. We are in British Columbia, so a very wet area. And also they applied some forms of water protective coating on the CLT floors. There were other strategies, including monitoring. So they installed some sensors to evaluate the presence of the moisture content into wood. As I mentioned, wood absorb water from the environment, and of course also if there is some bulk water like from precipitation, it becomes wet, and you want to avoid the presence of too much moisture in wood before enclosing the building, because otherwise then there will be this built up moisture that may affect performance of the building in service. So they installed these sensors that I believe are still collecting data to keep track of the moisture content during construction and avoid the presence of built up moisture. A lot of strategies were used in this building, and now from these lessons learned, they have been applied in other projects.
Tenemos una última pregunta para ti, María Paula, si lo puedes responder. Es del profesor Andrés Aranda. Su pregunta habla del sistema timber framing. Yo tengo entendido que debe ser el mass timber, porque pregunta sobre la fabricación de los elementos se podría unir con adhesivo sintético ordinario. Lo que parece por la pregunta, tal vez por la... es de tipo el glue lam o el mass timber, no, la CLT. Si el adhesivo tiene que ser con adhesivo sintético ordinario, es un adhesivo especial. Tal vez tú podrías en pocas palabras explicar un poco cómo es el sistema de pegado y prensado de esos materiales, ¿no?
Sorry, I couldn't hear. But could you repeat the question, because the voice was... Can you repeat it again?
Okay. El sistema de mass timber, la fabricación de los elementos se podría unir con adhesivo sintético ordinario.
Well, there are different types of adhesives that can be used. Some are more appropriate for environments, for wet environments, and some are commonly used, and these are the most common, and in interiors. And also there has been a strive to have brighter adhesives to improve the visual appearance of wood. So the most common, which is this light colored type of adhesive, is so-called PUR, but then we have also other type of so melanite, formaldehyde, and I'm sure Michael after me will talk more about specifications for adhesives as well. But there are a few standard ones, and depending also on the material, like the wood species, the application for exterior or interior, so then basically the type of climate they're exposed to, and the aesthetic visual requirements.
Perfecto. Bueno, María Paula, quisiera agradecerte inmensamente por la oportunidad de dictar esa charla muy especial, muy llena de contenido el día de hoy. Es un inmenso placer poder contar con la participación de la OSU, la Oregon State University, en el día de hoy, y queremos, lógicamente, continuar esa relación que iniciamos el mes pasado, estableciendo investigaciones y poder implementar aún más el uso de la madera aquí en Latinoamérica, en específico en el Perú. Muchísimas gracias. Grazie di cuore per essere qua e ci sentiamo.
Thank you all for hosting me, and I wish you a continuation of this series of seminar and meetings. And you can share my contacts to any interest people in the audience if they have other questions or any interest. Feel free to reach out. And looking forward to more collaborations in the future.
Gracias.
Thank you. Bye.
Muy bien. Continuamos con la siguiente ponencia de la jornada y cerrando el tema de la madera con Michael Thrail-Kill, que es el propietario del estudio de mismo nombre, M. Thrail-Kill, que es una empresa de arquitectura que da servicios desde proyectos, como también consultorías internas, design de interiores y de landscape, a toda la región norte-oeste de Estados Unidos, también de otras partes, ¿ya? Michael, bienvenido y puedes empezar con tu presentación.
Great. I'm happy to be here. Thank you for bringing me. I'm very happy to be presenting to this group. The work that we're doing in mass timber specifically, which is what I'll be talking about, is developments that are built upon the research and development of these systems, mainly originally in the Tyrol region of southern Austria and northern Italy, and then continuing in the Scandinavian countries and Benelux countries. And then these materials made their way to North America, primarily the Pacific Northwest of British Columbia and Oregon and Washington. But I'm very happy that other parts of the world are becoming interested in this, that they see the potential, and that in Peru, you're striving to understand this better, developing relationships, and hopefully bringing this practice, further afield. Of course, as I'll talk about, we see this is also happening in New Zealand and Australia. It's happening in Southern Africa. And more in Southeast Asia. Obviously, these are some of the largest and growing markets and the most potential to penetrate those markets and hopefully cut the carbon growth that's occurring through these buildings. So I'll talk about that. But the first thing is I just want to applaud the fact that you're here and you're listening. And we have an opportunity to share what we have and look forward to hearing how these things develop in Central and South America. So I'm Michael Thrail-Kill. I'm the founder and the owner of a small practice in Portland, Oregon. We produce specifications for other architecture firms. So these are the technical written documents that accompany the drawings that the architect produces. And these documents.
¿En inglés?
I'm sorry?
¿Una estudiante quiere que ponga en inglés? ¿Mejor? ¿Preguntó algo? No.
Should I speak slower? Is there a problem with the translation?
No, ninguno.
Okay. So the practice that we're doing, providing specifications to architects, includes firms in the Pacific Northwest, as well as throughout California, Florida, Virginia, New York, Colorado, as well as some projects with these firms overseas. My firm currently is about 15 people. Most of them are located here in the Pacific Northwest. 2 of them are in Argentina. We've been doing this practice for 8 years. We're involved in many different states, a few countries. We've produced over 500 projects during that time and probably published over 2,000 project manuals. These are some of the clients that we've been working with in the past and currently. So it's a large exposure through these clients to the entire width of available architecture projects, from airports and train stations to universities and dormitories, multifamily housing, single-family housing, office.
Sorry, Michael, sorry, you're not sharing your screen.
I'm sorry. Okay, excuse me. Let me break out. I'm sorry, I've been proceeding for a little bit here without.
So now I can see your screen.
Yeah, okay, let me start again. Excuse me. So here's me. We don't need to see that too much. And then this is our team here and a few others, and the firms that we're working with. The beauty of working with so many different architects is that we are exploring a broad variety of project types, as I described, as well as construction systems, and exposed to all of the different engineers that are involved with these architects, learning about different ways to apply mass timber. So my discussion today will be a little more focused than our previous presenter, and focusing down onto mass timber itself and the variety of systems that are available there. Maria Paola discussed these, I think, in a good overview, and I'll try to get more deeply into that. The main reason we are pursuing this alternative structural system to, say, steel or concrete is for the capacity to sequester carbon, so that trees, or as one of the questioners talked about, other organic matter like bamboo, absorb carbon during the normal growth process. Let's say in the case of trees, the trees we're using are typically 30 to 40 years old. So they have absorbed carbon during that time. They are harvested. There's obviously an expending of carbon through the harvesting process, the cutting, the trimming, the assembly of panels and other members, and the transport to the site and the installation. But at that point, that sequestered carbon is locked into the building. One hopes for 100 or perhaps 200 years. And that carbon held there will allow us the time necessary to develop different transportation systems and other things, energy production and such. What's intriguing is that while we're looking for these other solutions for transportation and energy production and manufacturing processes that use less carbon, we have this method that's working very well to immediately begin sequestering carbon that's been taken up over the past 30 to 40 years and continues to be absorbed. So the thing that will be important in order for mass timber to be utilized broadly would be for the systems that we're talking about to be widely accepted. And clearly the most important factor there would be to convince code authorities and authorities having jurisdiction over standards and requirements that they are convinced that these systems are safe, that they're appropriate, that they withstand fire, withstand earthquakes. And so one of the primary things I'll be addressing will be the prevalence of standards and requirements for the materials, the glues, the species of wood, etc. The projects we've already been utilizing mass timber on are broad. As I mentioned, we're not only working on all these different types of projects across various structural systems, we've utilized mass timber in over 80 projects that we've been involved with so far. And these are for all types of buildings. All the ones shown here use mass timber. In some cases, it's quite visible coming outside the building envelope and supporting the structure here. In most cases, however, the structure is within the building envelope and protected from the weather. This is clearly a concern in the Pacific Northwest because it's quite wet here a lot of the times of the year. But even in South Florida where we work, obviously we have a lot of moisture as well as heat and termites and other insects. And so keeping the wood inside the building envelope is the primary strategy to preserve it. Here's some just real photographic examples of projects that we've been working on. Maria Paola talked about the kind of hybrid systems of something like maybe precast concrete with with composite glulam beams and CLT decks. In other cases, a fully wood building like this recreation center, just the structure and roof of an airport terminal, the two buildings, the research department and the teaching departments at Oregon State. So there's many examples of this being used, a hybrid of steel and wood in the case of a project down in Los Angeles. So these projects, they cover all aspects of construction and project types that we've been working on. So the overview I'm going to give you of mass timber is going to talk about the types of mass timber panels, the standards that we use to regulate those, the various species and grades and layups that we use, the various appearance classifications that we call for, fabrication and tolerance requirements. We'll speak about adhesives, fasteners, and connectors. We'll talk about delegated design and what that means. We'll speak about the coordination and shop drawing process between the bidders and contractors and the architect. We'll speak about method statements, sealers and finishes to protect the wood, and about fire-rated connections. First of all, I want to explore the types of mass timber. We have cross-laminated timber, dowel laminated, nail laminated, glued laminated, and structural composite, sometimes referred to as mass plywood. The standards that we see are broad ones that cover mass timber in general, as well as very focused standards for everything from adhesive to fasteners and grades of wood. As this, the use of this material has increased in the North American market since about 2008, 2009, as we saw projects such as the one in Vancouver and others sort of set the stage for this development. And since that time, we've had multiple generations of documents that support that. One of the primary one is the ANSI 117, which is this one here, which is updated every 2 to 3 years, the most recent one having been 2020. We also have produced by the Wood Products Council a mass timber design manual that is a little more user-friendly and a good introduction to the standards. The National Design Specifications for the United States, also by the American Wood Council, and then a similar parallel document in Canada, the CSA 086, which is the engineering design in wood. All of these I can make available in a zip file that have as many of these as I was able to grab free online, and I'll provide those for people to be able to see. Within the mass timber types, the first one I talked about was cross-laminated timber. This is a product that initiated its existence in, as I mentioned, northern Italy, southern Austria, laying up approximately 50 millimeter by 150 millimeter pieces of wood into alternating direction lamellas. And the standard that applies directly to this particular product is the ANSI standard for performance rated cross-laminated timber. These panels are graded not only for the quality of the wood, but also the appearance. And so far, we have many different species that have been approved for use, a good number of those that are regularly grown and harvested in South America. So the standard is pretty well developed and cross-searchable and applicable to things such as radiata pine and other species that are similar to those reviewed in the standard. Cross-laminated timber can be used and has been used primarily as a vertical force-resisting element as a floor panel, but increasingly is being used as a vertical element for lateral shear, as well as conducting gravity forces down to foundation. There's a very good standard that the state of Oregon has developed, the statewide alternative method, which provides very good guidance for seismic force resistance in lateral forces. So it's definitely important that certain state bodies are developing their own standards, often because of the benefit to that state's forests and forestry industry that they develop these standards. But other states as well, Arkansas, the province of British Columbia, and others have developed standards. And eventually these will probably be turned into national standards. But obviously it was important that states develop these on their own to protect their own forestry markets. Similarly, I expect that perhaps provinces or individual countries within South America will develop standards, and then those will become more regional or international standards over time. The second type of product I'd like to talk about are Dow laminated timbers. These are completely wood systems. They can be done with adhesive or without. They consist primarily of a softwood vertical oriented member that then has a hardwood dowel driven through pre-drilled holes. These are usually done as built up panels about 70 centimeters to maybe 2 or 3 meters in width, and perhaps 5 to 10 meters in length. They're delivered to the project site and then installed, compositely across the surface as a horizontal deck. The image you have shown here is actually upside down from the final installation. This one's shown with a groove routed into the bottom of each of the members before they're assembled. And this provides a certain aesthetic quality. It prevents the appearance of cracking between or gaps opening between the individual members, and provides a little bit of acoustic improvement as well. So normally this surface would be the visible surface facing downward. There is a standard for this. It's recognized in the standard ICC evaluation reports, such as one that the manufacturer Structurecraft had developed, the ESR 4069. So like the states I discussed earlier that develop their own standards to promote their own industry, sometimes when a standard is lacking, an industry participant like a manufacturer may promote themselves by financing a study that then becomes a standard over time. Another example of this would be nail laminated timber. Intriguingly, nail laminated timber, which are multiple vertically oriented solid lumber members that are nailed together, is a very old system. It was originally used for warehouse storage flooring all over the North American region in the early 1900s. Many of the older buildings that we renovate in Portland that were originally warehouse buildings are being turned into apartments or offices, often have very dense, thick, nail laminated wood decks, which are obviously quite attractive to see from below, and end up being protected on the top side with a thin layer of concrete to provide fire protection. There are some standards for this, including the Nail Laminated Timber U.S. Design and Construction Guide. This is, as I say, a quite old standard, in fact, so it really relies on the species of the wood standard as well as the quality of the steel nail that's used. These can be done on site with individual layers laminated together one at a time, or they can be done in a factory increasingly as panels similar to the Dow laminated timber. The next one I'd like to speak about is glue laminated timber, and these are very common as horizontal and vertical structural members, beams and columns primarily. We've been using these both in straight and curved forms as columns and beams in buildings in the United States since the 1940s or so. Increasingly, these are being married together with additional adhesive between them to form panels used horizontally. The standard that's used has been around for a long time and developed, as I say, every 5 to 10 years. Currently, that's the ANSI 190 product standard for structural glue laminated timber. This was primarily a standard developed for use of the members in vertical and horizontal framing, but also has added articles now regarding the use as a composite horizontal deck. The intriguing thing about glue laminated timber is the ability to curve the members and produce quite dramatic structural systems that can be exposed to view. And obviously a quite extreme example here, creating a very interesting building structure. Another mass timber system is structural composite lumber. This exists in a variety of types. Maria Paola had a very good slide showing the variety of ways that a tree can be pulled apart and its individual pieces used. We've gotten quite good at peeling logs, peeling off a thin layer of a rotating log to create the veneers used for LVL. Those are then built up into panels that we sometimes refer to as massed plywood panels. The wood can be chopped into pieces that are then used as parallel strands. And the definition for a parallel strand would be that the ratio of the width to the length of the strand is about 1 to 300. A laminated strand lumber is a similar but smaller chopped element, basically a ratio of 1 to 150. And then oriented strand lumber is a ratio of 1 to 75. All of these can be married together, first laminated as fairly thin panels, and then those panels brought together to produce thicker sections for horizontal floor and roof plates, and those could be in the range of 20 to 40 centimeters even. The standards for that are the APA structural composite lumber selection specification. I'll talk a little bit more directly about mass plywood panels specifically, which, if you recall from the previous slide, is a version of the laminated veneer lumber. There are two large manufacturers currently, one here in Oregon, Frere Lumber, and another in Finland, Stora Enso. These two manufacturers have developed very good standards, including the one that Frere had developed. It's an ICCES evaluation report, the ESR 4759 that's here, and I can provide this later on. Essentially, what's done here is similar to the CLT. We have alternating orientations of the veneers. In this case, the orientation can be predominantly in one direction with a few plies in the opposite direction. We can see that in this image here, where most of the plies are laminated in the longitudinal direction of the panel, with a few plies going the other direction. And then these are built up as multiple thinner, about 2 to 2.5 centimeter thick panels, married together to produce something that could be in the range of 20 to 40 centimeters. These can be used, as shown in the image here, both horizontally and vertically as framing members, as well as horizontal panels for roofs and floors. There was a good question earlier about adhesives, and adhesives are important not only for the structural capacity of the wood, but they need to maintain their strength both during the high moisture periods of life of the wood. When the panels are originally adhered together, the adhesive needs to continue to perform as the moisture leaves that wood during its drying. Then the adhesive needs to maintain its strength even under situations where that panel or structural member may be exposed to moisture in the field. Additionally, the adhesive has to remain strong in the event of high temperature during a fire event. And also, we have some of our architects wanting that the adhesives are clear and not easily visible. And I'll talk about that a little bit later. the standards that are available for adhesives is the ANSI 405, Standard for Adhesive Use in Structural Glue Laminated Timber. Clearly, that's aimed originally at structural glue laminated timber. However, we are using that same standard for CLT and other mass timber products. There are a number of other standards within the ASTM standards that regulate moisture and durability of bond, and those are listed here, and I'll provide some of those. There are some additional adhesive standards that we've used over time, and this is because, as with any new construction material, standards have been developed in one location that may not be developed in the place where the product's being used. So working with local authorities at the beginning of our use of mass timber, we received some allowances to use European standards, such as Deutsche Industrial Norms or European norms that I've listed here. These grades of services were able to be incorporated into the National Design Standard first, and then we've developed North American standards with ASTM. The exterior exposure standard, if the glue lam or CLT or other mass timber is going to be outside the building envelope, is this ASTM D 2559. Additionally, we have some appearance requirements. We typically require that the glue be a white, clear glue instead of the dark brown glue that's sometimes used. The dark brown glue can be seen in the image on the left here, where the line between the lamellas is very visible because of the glue. That's less apparent in the image on the right due to the use of clear glue. The use of the clear glue allows the member to appear more monolithic. Either may be structurally preferable. Some of our architects actually like the appearance of the brown glue and the kind of industrial look of that, and others prefer the more architecturally aesthetic of clear glue. We also have some premium appearance requirements that relate to the glue laminations, where we require that knots either not be present or that they be cut out and filled with a wood-colored filler or putty or some sort of clear wood insert, similar to appearance-grade plywood. There was a question earlier with regard to the protection of mass timber from fire. And as Maria Paula noted, the method that was used in the beginning of mass timber, both in the Tyrol region, in Scandinavia and Benelux, as well as British Columbia, was to simply encapsulate the wood framing and decks with gypsum board materials, multiple layers. And this was done because there already was a developed standard for how to protect wood framing from fire using those same gypsum board materials. However, one thing that was well understood with regard to mass timber, and this has to do with solid lumber timber, quite large members that were used, from all throughout the 18 and 1900s, were large members used in factories and in warehouses, in barns, in churches. And it was understood that those large members could be exposed to fire for a certain amount of time and still retain their strength. As demonstrated in the image here, a fire-tested, quite large member. This member is likely about half a meter by half meter, 50 by 50. When exposed to fire over 3 hours, becomes a member that is about 2/3 of that size, still protected inside. So in essence, the structural engineer could design for a final strength that after fire still supports the building by specifying a larger member. That larger member exposed to fire becomes a smaller member, but continues to support the building after 3 hours, allowing occupants to egress the building, and even allowing fire personnel to come in and put out the fire without danger of the building collapsing. These standards have been tested significantly since about 2015. We've had regular fire testing of these assemblies in a variety of composite arrangements, up to 2 and 3 hours. So these fire testing standards right now are the ASTM E119 in the US, or for Canada, the UN ELCS 105. There is additional specific high temperature testing for adhesives, which are these two United States and Canadian standards here. The importance of the adhesives is that as the fire progresses and burns its way into the wood, that the adhesive between the layers does not fail and the member then begin to buckle because the layers are not adhered together anymore. So that's the reason to specifically fire test the adhesive itself, as well as the performance of the wood. The testing for CLT products is this one here. I'm not going to keep reading all these numbers. But the importance was that the individual lamellas of the CLT don't peel away during the course of the fire. That's for two reasons. One, so that the structural integrity of the panel is maintained by the lamellas being attached. But also, if the lamellas burned and fell away, they would expose a new layer of fresh wood to the fire. And we want the original layer to remain there, acting as the fire protective layer. In the latest international building codes, they specifically require that CLT be protected with the new adhesives to avoid char delamination. Char is the term for this burned through layer that typically is about maybe 10 to 20 millimeters thick. Also important, obviously, are the fasteners and connectors that we use. We have a very good standard now for the dowel type threaded fasteners that we're using. These fasteners used throughout the process, both to connect the panels to the structural members and to connect the various connector plates to the members, all fall within this standard. The connectors I'm referring to here are essentially steel plates and buckets and brackets that are usually custom fabricated for each project, and they use standard ASTM steel standards and galvanizing standards here. I spoke earlier, or said I would talk about delegated design. Delegated design is a standard that we use in the United States, especially for new structural systems where the project structural engineers may not be familiar with how to design with a new product. In this case, the manufacturer would provide the engineering for the members, as they're going to be more familiar with that than the project structural engineers. This is something that over time will go away as structural engineers become as familiar with mass timber as they are with steel and concrete. I don't expect to see so much full system engineering as we've been calling for in the past 10 years or so. However, one aspect of the products that will continue to be delegated design is the erection, rigging, and bracing. So that means how, when the product is brought to the job site, is it lifted into place, attached both temporarily and permanently, and how is it braced temporarily until the building structure is complete. Also important in the relationship between the manufacturers and the engineers and architects are the shop drawings. In this case, the manufacturer or fabricator is responsible to provide computer-generated designs for each member of the building, both the horizontal plate, like we see engineered here, or the vertical and horizontal members, supporting members, including potentially the interface with steel structure that may be used for seismic or other lateral force control. The shop drawings are produced by a professional engineer employed by the mass timber manufacturer, and they are signed and sealed by that manufacturer's engineer. The shop drawings can be produced in a variety of levels of detail. Usually at the start of the project, they're in the LOD 100 to 200 level. This is an international standard that determines, the amount of detail involved. In this case, this image is showing a precast concrete column where you see just a standard understanding of vertical force, beginning to understand how the transfer of other vertical forces into that vertical member, the beginning of understanding at LOD 350 of additional composite materials in the case of the reinforcing bars in this concrete column, and then finally the full reinforcing in concrete at an LOD 400. In the case of a mass timber system, this is an LOD 300 detail, which brings in not only the vertical load transfer member, but also the horizontal deck, and any additional horizontal decks and transfer members that may be used throughout the project. We typically expect an LOD 300 to apply to slab plans and connections. The LOD 350 begins to lay out the panels themselves and to call for sleeving for mechanical, electrical, plumbing systems. And then a level LOD 400 would be for the single piece shop drawings of each individual member. And it says this is an LOD 400 drawing here. We also have a lot of interface work that we're doing within the design team, where the mechanical, electrical, plumbing engineers are working closely with the structural engineers and even the architect to generate three-dimensional modeling that ensures that everything's going to come together without interference. Coordination drawings are, in essence, what I just spoke about. This would be drawings that the manufacturer of the mass timber elements, the general contractor, and possibly working with the design teams, architects and engineers, to once again generate a coordination model or drawing that brings in all the elements of the building, but even begins to anticipate loading of a truck so that when it arrives on site, the members that are on top are the first ones that need to be erected, and then proceeding through the load. It's quite common that part of the coordination drawing sets are the loading diagrams showing how 50 or 60 loads of mass timber materials are loaded at a factory or a fabricator, brought to the job site on a regular basis, and then unloaded and taken away. Method statements are something we include in the specifications, which lay out the responsibility and requirements for bracing the structure during its erection, such as the example here where we have cross braces that are temporarily attached. We also talk about how those can be attached because we like the appearance of the wood and we want to leave the wood exposed, and we want the fasteners that are used not to damage that wood. A rigging plan also needs to be provided by the contractor, which show how they're going to attach and lift and place these members into position during the construction. One thing I went over a little bit too quickly during my discussion about fire protection. The reason that we were interested in North America to do the fire testing rather than simply wrapping the members in gypsum board was that the appearance of the wood is a pleasant thing that we'd like to take advantage of. Being able to see the underside of the wood deck, the columns and beams, is an attractive aspect that creates a warm and inviting environment. Clearly, this is something that's kind of moving back to other parts of the world as well. Equally in Europe and Australia, New Zealand, South Africa, they are utilizing their own fire testing to prove that the wood can exist on its own without additional gypsum layers or other types of fireproofing coatings or treatments, so that the wood can be experienced, as an attractive element in the building. Obviously, that also saves cost. We don't have to wrap all these materials with gypsum board or other finishes, which reduces cost and carbon impact and everything else. Included in the method statements, jumping back to that issue is a water or weather and moisture protection plan. Basically, we require the contractor to let us know how are they going to keep the building dry, so that during construction, we don't have moisture on the deck that leaks through the joints and comes down below, bringing with it staining and rust and dirt. This is always a problem if you start to marry steel with wood. The steel on the job site is typically not coated and begins to rust almost immediately and begins to stain the materials elsewhere in the building. Since this ceiling won't be covered by gypsum board or an acoustic ceiling system, the contractor had to go back and individually sand and clean all of these members to get them to appear appropriate. There are some standards with regard to CLT for the grades and species of wood. I talked earlier about the wide variety of species available. These are all North American species originally, but I know that many of them are planted in other parts of the world, or other products such as radiata pine, other species may perform quite similarly to southern yellow pine or Doug fir larch. So these are the variety of species that we see. There's also a visual grading of the various types. The typical for the exposed CLT is visual 1, the most standard. A higher grade could be visual 2, but we find that the cost of that is prohibitive. So then we would say the stress grade is V1, with the longitudinal layers being number 2 Doug fir and the transverse layers being number 3 Doug fir. There's some appearance classifications. We speak of architectural appearance, which is obviously where we're exposing and we want a nice look to the wood. In this case, the face layer is free of knots and other deformities. Again, that only applies to the face layer. The concealed layers could be a lower quality as long as they meet the engineering standard necessary. All knots and holes would be filled, and all exposed surfaces are sanded smooth, and the edge joints are tight during the manufacturing. What that means is that the presses they use to squeeze the panels vertically and push them together also have a sideward pressure to push the panels together and keep the members aligned. An industrial appearance obviously would be an allowance for knots and other deformities. Scratches and damage to the wood may be acceptable to a certain degree. Dow laminated timber has similar standards. We have species of Doug fir and spruce. The profiles, as I mentioned earlier, can be altered in order to create various acoustic performance. This acoustic performance isn't substantially improved. It's something like a 0.80 STC for those who understand that. But it is better than the raw wood. We've seen this used in libraries and other spaces that don't need a very high acoustic performance, but some improvement is desired. Nail laminated timber similarly is available in all of the species that we're familiar with. And in fact, here's a good example of a nail laminated timber deck. What's intriguing about this product, because of the individual layers screwed or nailed together, is that they're able to follow a curve, such as in this transit station in Vancouver, BC. The glue laminated timber species again are here. I'm sorry. For glue laminated timber, we see the same types of species as we saw for CLT. The difference between cross laminated and standard glue laminated is a continuous longitudinal orientation for glue laminated, and obviously changing the orientation in cross laminated. The structural composite lumber would be like the mass plywood. We have some standards here with regard to a standard architectural appearance where it's very clean. And then we even have an upgraded architectural appearance, which avoids knots and limits the number of defects for the area. Again, here's an image of how those are used, using a upgraded architectural appearance for a quite nice looking material. Fabrication tolerances are very important. The fabrication process for milling the wood and basically creating the ends of the members, the particular cuts across the members, and the holes that are drilled are done with a very high precision computer numerically controlled, or a CNC machine. The tolerance is in the range of 1.5 millimeters. So the wood tends to be very high tolerance compared to other fabrication and structural systems. More specifically, the thickness is within basically a 2% of panel thickness, or about 1.5 millimeters. The width of the panel, about 3 millimeters. The length within 6 millimeters. The squareness, again, within 3 millimeters. And the straightness, again, within 1.5 millimeters. These are our standards for mass timber. The difficulty is when we meet a piece of steel or concrete in the building. The steel standard is more in the range of about 6 millimeters, and concrete as much as 12 to 25 millimeters. So you can imagine when steel comes against concrete, we need to require that the steel or the concrete have a tighter than normal tolerance to ensure that the members come together, or slotted systems or other means of adjusting for inconsistency in the field have to be incorporated. Sealers and finishes are important both for the protection of the wood during the construction and its appearance following construction. As Maria Paola noted, in the factory, they can apply either a coating, a liquid coating, or a self-adhered membrane. We often request that that be installed in the factory before the panels arrive on site. And this is so that once they're on the site, we don't have as much moisture moving into and through the panels and staining the materials down below, but also simply in our environment here with so much moisture, to avoid the excessive moisture and potential for mold or other problems inside the building later. There are both interior and exterior finishes, some of which can be UV resistive or last a long time when exposed to rain and the weather. The fire rated connections are really important. I spoke earlier about the charring of the wood, but we also, where we have joints, can introduce a groove in the end of the member within which we insert intumescent material. And that intumescent material, in the case of heat, expands and chars as well and forms a seal right here to protect the metal hanging element. So this hanging element, this connector, which I spoke of earlier, but I didn't have an image of, is what marries the beam to the column, or one beam to the next. You can see that this one's quite sophisticated. It's individually adjustable from above to allow the beam to be minutely adjusted to stand square and tight to the adjacent column or beam. The standards that we're using are the technical report number 10 for calculating fire resistance. And then for Canada, there's the Annex B of the CSA fire resistance for wood elements. Both of these take care of the connectors as well. This is an example of the intumescent strip. In this case, we have a very large column with a recessed, routed out area to receive hangers. A beam will come into this location. The beam is likely as wide as the column. There's a groove for intumescent material to be laid in. And this will arrive on the job site appearing just like this. The beam will be brought in having very similar but inversely hung hangers that marry in, so that this male member on the beam will attach into this groove, and the groove on the beam will hang over this pin here. So in essence, the top of the column is pointing up this way, the bottom of the column this way, and the beam hangs downward on these connectors. What's important to notice here is that the wood on the outside is protecting the steel connectors or aluminum, which is an intriguing thought, that the wood is protecting the steel. So that's the full presentation with regard to how the how the various standards and requirements that we specify come into play. We spoke about grades of materials, the types of various mass timber systems, the adhesives that are involved, the finishes we use, the connectors and fasteners. And I invite any questions you have. Looks like some may be coming up here.
¿Alguna pregunta? Any questions? We have one question from our Dean Professor here about what kind of software do you use for these mass timber structures you put on the in your slide.
I have to admit, I'm not an engineer. I'm a specifier. So I'm happy. I will ask that question of our engineers, and I'll let you know later on. We are the written documents that we're writing are written in Microsoft Word. So we're not using anything sophisticated to write the written document. Obviously, there are quite sophisticated three-dimensional modeling tools, and we'll get the names of those for you.
Okay, thank you. Tenemos otra pregunta aquí. ¿Podría compartir alguna ¿hay formación técnica especializada para armado de estructuras en madera?
Yes. I know that the forestry program at Oregon State University, as well as at University of British Columbia and others, obviously are preparing students within the forestry industry to provide the raw materials we need from a forest perspective. Within the engineering departments of the same universities, I hope that there is some sharing of knowledge between the forestry department, perhaps, and the engineering departments. Obviously, within the engineering firms themselves, they are developing standards and sending their staff to various symposia, conferences, etc., to learn this. Again, though, this isn't the actual engineering design of these systems is not my specialty. So I will ask a couple of local Holmes and KPFF structural engineers how they've seen their recent graduates who come on to their staff, how well they're learning these systems in school.
Okay. We have another question from Fabiana. What's the most common issues in a construction with wood and how we can prevent them?
Okay. Some of the things that happen are very good, and some of them can be a problem. The very good thing is that it looks beautiful. I think the wood is a lot more attractive than raw steel or concrete. So the main concern we have is not actually the structural issues, but rather how can we continue to maintain the appearance of the wood so that when the project is finished, it's actually nice looking. And that's our biggest challenge, is how do we keep the wood looking good so that we can continue to keep it exposed and not cover it up. However, there are some other challenges. I've been actively pushing our clients in Florida to consider using mass timber on their projects. And there's a very natural reluctance to move away from concrete construction that's very well known in Florida. The immediate reaction is the wood is going to rot, there's going to be insects. And so I try to connect them to architects and engineers in Brazil that I'm aware of that are doing wood in a similar environment. And simply trying to, I think the next problem we have is trying to bridge that gap of understanding and reluctance to use a new system. Those are the two main concerns, is reluctance and maintaining the appearance and keeping it looking good.
Great. Well, Michael,
clearly one thing there though, the main concerns had been fire, and I think we've dealt with fire very well. That would have been the main concern, obviously. And that's the first thing people say when we have a 17-story wood building, how is it protected from fire? And I think we have great testing that has understood that. The next one might be seismic performance. And most recently, I'm sure you're all aware of the studies being done right now on a 10-story structure on a shake table at the University of San Diego, University of California, San Diego, where they are actively testing a variety of hybrid and fully mass timber systems in this 10-story structure for seismic resistance.
Great, great. Well, Michael, we don't have more questions, so I'd like to thank you for your presentation today. It was very instructive, and I hope we can get along with this collaboration for further work together with our university in your studio.
Yeah. And I know you're aware, but all the students should be aware, there is CLT being manufactured in South America, both in Brazil and in Uruguay now.
Yeah.
So there is local material being produced, and I look forward to seeing these projects increase there.
Great, 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 great. Okay. Thank you, Michael, again. And now I'm going to just do a message for my students. Bueno, chicos, muchas gracias por la participación de todos. Continuamos con la presentación de nuestra semana. Hoy día por la noche tenemos la presentación, la charla del profesor Theo Tab sobre espacios de transición, Thin Spaces, el profesor emérito de la Universidad AM de Texas, en Estados Unidos. Entonces espero poder contar con la participación de todos a las 7 p.m. Muchísimas gracias por la excelente jornada que hemos tenido, la participación de cada uno durante todo el evento. Nos vemos más tarde. Chao, chao.